Okay, you can start the review now.
All right, guys, welcome to 230 Final Review by FSCTC. I'm Charan Nadiminti, and there are two more tutors, Veda and Martin, will be taking over at the final exam review. Today, I'll be walking you through Chapter 4, which covers multi-cycle and single-cycle processor implementations. These are two fundamental approaches to design CPU data paths, and understanding them is crucial for computer architecture. By the end of this presentation, you'll understand how instructions flow through both implementations and the key differences between them, and how to calculate execution times for both of them. All right, let's dive in. Okay, let's start with the multi-cycle implementation. The key idea here is that we break down instruction execution into multiple clock cycles, with each cycle performing a single specific task. Looking at this data path diagram, you can see several key components: the PC, instruction memory, register file, ALU, data memory, and various control signals. The orange highlighting shows the control unit managing everything. The beauty of multi-cycle implementation is that different instructions can take different number of cycles. Simple instructions like jumps take fewer cycles, while complex ones like load word take more. This is more efficient than forcing every instruction to take the same amount of time, which happens in single cycle. All right, let's go to the next slide. Sorry. Yeah. Okay. Every instruction in multi-cycle implementation goes through up to 5 stages. Let me walk you through each one. Step one, instruction fetch. In the first step, we fetch the instruction from memory using the PC, and we update the PC to PC plus 4. This happens for every single instruction, no exceptions. Step two, instruction decode and register read. Here we decode the instruction and read any necessary register values. We also read immediate values if needed. Notice that J-type instructions don't really need this step, but we do it anyway for consistency. Execution, memory address calculation, or branch is third step. This is where things diverge based on instruction type. For R type and I type instruction, the ALU performs the actual operation. For load and store, we calculate the memory address. For branches, we check the condition and calculate the target address. For jumps, we just calculate the target address. And then step four, memory access or R-type completion. R-type instructions write their ALU result back to the register file. Load and store instructions access memory, reading or writing respectively. And then step five, the last one, memory read completion. This final step only applies to load word instructions. We take the value from memory and write it to the destination register. Okay, let's walk through an example. Okay, this is LW step one. Load word example. Let me show you a concrete example with the load word instruction, which uses all 5 steps. Step one, the yellow highlighting, as you can see in this slide, shows the active path. We are fetching the instruction and updating the PC. Notice the control signals. Um, Here it's one. Yeah, notice the control. We're fetching the instruction and updating the PC. Notice the control signals. PC write is one, mem read is one, IR write is one. Step two. Oops, yeah. Step two. We are now reading from the register file. The ALU SRCB is set to 11 to read the registers. The instruction is decoded. Let's go to step three. Step 3, the ALU calculates the memory address by adding the base register value with the offset. ALU SRCB is now 10 to select the immediate value, and ALU SRCA is 1 to select the register. Next step. We access memory using the calculated addresses. Memread is 1, IRD is 1 to use the ALU output as the address. Step 5. Oops. Yeah, step 5. Finally, we write the value from memory into the destination register. REG write is 1, Mem to register, right? Mem to register is 1, register destination is 0 to select RT as the destination. Okay, clock cycles and timings. Now let's talk about timing. Looking at this table, different instructions require different number of clock cycles. Jump, branch, and BQ 3 clock cycles. R type and I type and SW require 4 clock cycles. Load word requires 5 clock cycles. The clock period is determined by the slowest component in any single stage. In this case, that's the necessary memory unit at 5 nanoseconds. So one clock period equals 5 nanoseconds. Let's calculate execution time for this program. So we are having 4 here, and then 4 cycles again, and then 3 cycles. So the formula is 20 plus 20 plus 15 times the number of loop iterations. So that's 55 nanoseconds per iteration. Right, okay, let's go on. Okay, I have some questions here. It would be great if you could answer them either by muting or putting the answers in the chat. Okay, which of the following mapping instructions which of the following mapping between instructions and number of clock cycles for the completion of instructions are true? And we're talking about multi-cycle implementation. So if you have your answers, please put them down in the comments or I'll go through them. I think we have comments. Okay, people are saying it's ABD. Yep, that's right. Yeah, I'm gonna walk them through. First, add 4 cycles: instruction fetch, decode, register read, ALU operation, write result to register. So add 4 clock cycles. That's correct. And then LW 5 clock cycles. We just went through that. That's correct. SW 1 clock cycle. No, it should be 4. That's wrong. So C is the wrong answer. J 3 clock cycles. Yep, that's what we just went through in the slides. And the 3 clock cycles exactly are instruction fetch, decode, calculate target address and jump. And then BNE 2 clock cycles. No, it's wrong. It should be 3 clock cycles, which are instruction fetch, decode, register, read, check condition, and calculate target. All right, next question. Okay, which of the following are true about instruction fetch? That is step 1 in multi-cycle implementation. There are more than one correct answers in this. So if you want to place your answers in the chat. Okay. All right, I'll go through them. So the answers are A and D, and I'll tell you why they're correct. Explanation, instruction register is used. The fetched instruction is stored in the IR for later stages. And then why D is correct. PC value is updated to default value PC plus 4. Every instruction fetch increments PC by 4 points to the next instruction, as we have just went through that. Right. Okay, the next question. Which of the following are true about instruction decode? That is step 2 in multi-cycle implementation. Again, more than one correct. And the correct answers here are B and E. Let me go through why those are correct. So B, the ALU writes to ALU out register. The ALU performs a calculation and stores it in ALU out for potential later use. And why E is correct. All instructions perform the exact same task in the step. Every instruction reads registers and prepares values regardless of type. E. All right, next go to next one. Which of the following are possible tasks accomplished in step 3 of the multi-cycle implementation? Again, one or more are correct. And the answers are A, B, C, D. So ALU operation, R type instructions, add sub or etc. I type instructions, add I, etc. And memory address calculation, LWSW, base address plus offset, branch condition check, BQ, BNE, compare registers and determine if branch is taken. Target address calculation, branch PC plus 4, jump PC address times 4, and yep. We have one more question here. Which of the following are possible tasks accomplished in step 4 of the multi-cycle implementation? One or more correct. The answers are B and C, also D as well. Yeah, B, C, D. I'll go through why these are correct. B, write value from memory to memory data register. LW instruction, read from memory into MDR. C, write value from ALU out to RT. ITAP instructions, write ALU result to RT. D, write value from ALU out to RD. R type instructions, write ALU result to RD. Let's go to single cycle implementation now. Okay, now let's contrast this with the single cycle implementation. The fundamental difference here is that every instruction completes in exactly one clock cycle. Looking at this data path, you'll notice it's more parallel. There are no intermediate registers like the instruction register or ALU out register that we have had in multi-cycle. Everything happens here simultaneously within one cycle. The advantage: simpler control logic, no state machine required. The disadvantages: the clock period must be long enough for the slowest instruction. Uh, that means every single jump instruction has to wait for a full clock cycle, even though it doesn't need that time. It is a less efficient model overall, but it's simpler to design and reason about. Okay, let's go. Yeah, practice problem. Let's work through this practice problem together. We have three tasks. Trace the data path for BQ, and then write the control path for SW. Calculate execution time for a program using both fixed and variable clock time cycle. And we have the program given with the latencies. Memory unit 3 nanoseconds, register file 2 nanoseconds, ALU 2.5. Okay, solution. For the BQ instruction, the data path shows everything in red, the active path. Starting from the PC, we fetch the instruction, read both source registers, RS and RT. The ALU subtracts them to check equality. The zero signal goes to the branch and branch A and D gate and gate. If they're equal, we take the branch using the calculated target address. Otherwise, we use PC plus 4. All right, the second part, SW control path. For the store word control signals, let me walk you through the key ones. ALU OP 00, we're doing addition. The next one, addition operation. X means we don't care, we're not writing to a register. And then ALU SRC is 1. You're using the immediate value. Memory to register, don't care. Branch, we're not branching, not jumping. PC source, use PC plus 4 as it is 0. Register write, now we are not writing. Mem read, now we are not reading. And mem write is 1, so we are writing to memory. Execution time for both fixed and variable clock cycle times. Okay, the clock period must accommodate the longest path. So R type and I type take 9.5, and then load word takes 12.5 nanoseconds, store word takes 10.5, so on and so forth. But the longest is load word, so this is our clock period. 12.5 nanoseconds is our clock period. So in a single cycle, every instruction takes 12.5 nanoseconds. For our program with two iterations, one add I takes 12.5 nanoseconds. Loop body, it has three instructions times two iterations, so that will be 75 nanoseconds. 6 times 12.5, which will be 12.5 plus 75, 87.5. So yeah, 87.5 nanoseconds. All right, we have some questions. Let's go through them. Okay, which of the following mapping between instructions and number of clock cycles for the completion of the instruction are true? And note the point that these are for single cycle instructions, implementation, sorry. Let me go through the correct ones. The correct answers are A, C, and D. And yeah, in single cycle implementation, every instruction exactly takes one clock cycle and nothing more than that. So if anything except one is a wrong answer here. So which of the following are true for a 32-bit 2 times 1 mux, 2 by 1 mux? And again, there are more than one correct answers. And the correct answers are B, D, E here. Let me go through them why they are correct. B, output matches the width of the inputs, so that's correct. And then D, 2 by 1 means two inputs, one output. So there are two inputs, yep, that's true. And one input, just as I said. So yeah, 2 by 1 means two inputs, one output. So that's correct. Next question. Which of the following are true about sign extension unit? One or more correct again. Okay, the correct answers are A, B, E. Sorry, A, B. My bad. So first one, size of input is 16 bits. Immediate field in I-type instructions is 16 bits, so that's correct. And then B, size of output is 32 bits. Must extend to full register width, so that's correct. A and B are correct. Let's go to the next question. Which of the following are possible next values of program counter? One or more correct again. So the correct answers are B, C, and D. First one, B, the correct formula for branch instruction, BQ, BNE, right? The immediate is assigned offset in words. And then C, sequential execution, the default for all non-branch or jump instructions. D, correct formula for J-type instructions, JL, takes upper 4 bits of PC and concatenates with 26-bit addresses times 4. Okay, we have one more question, one last one. Register file components. Which of the following basic element is present in the register file? One or more correct, and the correct answers are C and E. Okay, C. 5-bit decoder converts 5-bit register number into one hot encoding used during write to enable the correct register. And then E, D flip-flops. Each register is implemented as 32 D flip-flops, one per bit, stores the actual data and updates on clock edge. Okay, that's it. That's the end of my presentation, and I think Veda will take over.
Okay, is my screen visible? I'm sharing my screen.
Yes.
Okay. So if anyone has any questions, please drop them in the chat. The other tutors will try to answer you in the chat so that the review session isn't interrupted. But once all the reviews are done, like there is another chapter, the sixth chapter review after this one. So after that, if we have time, you guys can stay and ask your questions, unmute yourself, and we will try our best to answer them. Okay, so let's get started with Chapter 5, Direct Mapped and Associative Cache. Okay. In this in this chapter, I'm going to cover direct mapped caches and associative caches, concepts like cache mapping, address breakdown, tag, index, and offset. And also, I am going to cover performance metrics like hit rate, miss rate, AMAT, and I also have few practical problems related to this chapter in the end. But since we are running low on time, we only have 30 minutes. I'm going to just show the questions on the screen and also the answers. You guys can pause the recording whenever you like later when you're reviewing this and work them through. Okay, what is cache? Cache is a small, fast memory located near CPU to speed up access to frequently used data. It acts as a buffer between the fast CPU and slower main memory. Main memory is much slower than cache, creating a speed bottleneck. The purpose of cache is to reduce latency in accessing data stored in slow memory levels like RAM. By keeping the frequently accessed data closer to CPU, we are reducing the wait times. And also, cache stores data and instructions that are likely to be used soon, meaning you don't have to go through all levels to fetch few instructions or data that you might be using right now. And then we have types of cache. In that, we have four types. And the first type is direct mapped cache. Each memory block maps to one specific cache line. There's a fixed formula that determines where each block goes. So that is direct. And associative cache is more flexible, allowing a memory block to map to any cache line. This reduces conflicts but increases complexity. And moving on to fully associative cache, it has a fixed mapping. Any block can go into any cache line. Minimum flexibility but requires searching all lines, which is time-taking and not really anyone's first choice when implementing any structures. And then set associative cache. Memory blocks map to sets. Each set has multiple cache lines, and this is a compromise between direct mapped and fully associative. The choice impacts both performance and complexities of the hardware. To get the visuals of like how each of these cache structures look like, you guys can go through your lecture slides. I'm pretty sure you guys have it there. So yes, moving on. Direct mapped cache. It is one-to-one mapping. Each memory block maps to exactly one cache line. This means that there's no choice in placement. Simple, easy to implement with predictable memory to cache mapping. Given an address, we immediately know which cache line to check. And what are cache lines? Cache lines are the number of cache lines is like the number of cache lines determines the index size. So if there are more cache lines, then they require more number of indexes. And address breakdown. Memory address is divided into tag, index, and offset. Each field serves a specific purpose in locating data, but the limitation is that multiple memory blocks may map to the same cache line, causing conflicts. This is the main drawback that this direct mapped cache has. And moving, diving deep into address breakdown, memory addresses divided into tag, index, and offset, like we saw in the previous slide. These three fields work together to locate data in cache. Tag uniquely identifies the memory block. Since multiple blocks map to the same line, we need the tag to distinguish them. Index points to the specific cache line. It tells us exactly which line to check in the cache, and offset identifies the specific byte or word within a block. This lets us find the exact data within that cache line. And if we look at the example, for 16 blocks and 4 words per block, the address is split as follows. Offset, you always use this formula to find it. Log 2, 4 words per block, so we're doing log 2, 4, which equals to 2 bits. And index, we're gonna plug in 16 in place of 4, and we get 4 bits. And tag is how many our bits are remaining. That's how you divide the bits in an address. And what are hit and miss? Hit data is found in cache. Tag matches and valid bit is 1, and that's when you know it's a hit. Both conditions must be true. And for miss, data is not found in cache. Data must be fetched from main memory. This happens when either the valid bit is 0 or the tag doesn't match, meaning whatever the conditions that must be true for hit, one of them might be missing or something like that. This is the extra. Okay. Yeah. Conflict misses when multiple blocks map to the same cache line, which is the only drawback for direct map cache. is whenever that happens, that is called conflict miss. And then they keep evicting each other even if other cache lines are empty, which is a time-taking process. And we have an example problem here, but since we don't have time, I'll let you pause the video when you're watching the recording. So this is the problem, and there's also the solution there. So yeah. Okay, moving on to performance metrics in associative cache. Hit time, time taken to retrieve the data from cache, and AMAT for multi-level caches. Consider the hit time, miss rate at each cache level, and miss penalty. This is the formula for AMAT. You probably some of these values will be given to you, or you will be given values for you to calculate them. So everything will be in the question, so you don't have to worry about missing anything. Only thing you need to know is the formulas for every term you see in this line. And global miss rate is overall miss rate considering all levels of cache and main memory. And cache performance metrics. Now, hit rate is percentage of memory accesses that result in a hit. This tells us how effective a cache is, and the formula is right here. Hit rate is equals number of hits by number of memory accesses that uh, took to get to the hit rate. And then miss rate, percentage of accesses that results in a miss. Same for 1 minus hit rate is the same thing. And in this slides, I think the formula is being repeated, so please don't get confused with that. Just see where it starts repeating, so just avoid that. And yeah, now aim at. It still has the same meaning, the average time for accessing memory factoring in both hits and miss. And this is the formula for that. Now moving on to associative cache. Fully associative cache. Memory block can go into any cache line. This provides maximum flexibility in placement, most flexible but requires checking all lines for a match, which is not, which would not be the first priority. And the hardware must compare tags in parallel across all the lines. That's about fully associative. Now, set associative. Memory block maps to one of the sets in the cache, but within the set, it can be placed in any line. This balances flexibility with hardware costs. Benefits are reduces cache conflicts when multiple memory blocks map to the same cache line, and blocks that would fight for one spot in direct map can now coexist. Offers a better hit rate compared to direct map cache at the cost of more complex hardware. Now it's address breakdown. So address equals tag plus offset. This one doesn't have an index. And we have to search all the lines. Without an index, we must check every cache line to find our data. And set associative, address equals tag plus set index plus offset. The set index narrows down which set to check. Tag identifies the block, and this is used to verify we have the correct data. Set identifies which set the block belongs to. Each block maps to a specific set. We all know this. And offset identifies the word or byte within the block, same as in direct map. So for a four-way set associator, we have four cache lines per set, and the block can be in any of those four lines. And then here's another example problem, and we also have the solution. You guys can go through this one later. And cache replacement policies. Um, LRU is full form is least recently used, replaces the least recently accessed cache line. The assumption is that if you haven't used something recently, you won't need it soon, which means it will be removed from cache and its place is taken by some other memory block or some instruction or something like that. And FIFO, first in, first out, replaces the oldest block in the cache. This is simpler but doesn't consider access patterns. Random placement replaces a random block in cache. Surprisingly, effective. I mean, this is surprisingly effective despite being the simplest approach. And then its effect on performance. The choice of replacement policy impacts the hit rate and AMAT. LRU typically performs best, but it does cost more to implement. So that's about cash replacement policies. From here on, I'm gonna just pause 2 seconds on every slide. This first slide has the problem. This one also has the problem. And here are the corresponding solutions. This is the solution for problem one, and sorry, problem two. And this is the question for problem three. Its solution, problem four, solution, problem five, six, and that is it for chapter five. But while solving these questions, if you guys have any uh, doubts or something, or if you guys feel stuck, you can always email me. I'm going to drop the email in the chat once the chapter six review starts. So, yeah. Martin, are you ready to take over?
Yeah.
Let me just stop sharing my screen. Yep. You can go ahead now.
Yeah. Mm. So we're gonna go through the chapter six parallelism. So what are different types of parallelism? There are four main types of there are more four main types. Instruction level parallelism, where multiple instructions overlap using pipelining. Second is the data level parallelism, where the same operation is applied to large sets of data like vector operations. Then we have thread level parallelism, where programs are divided into threads that can run concurrently. And finally, we have process level parallelism, where entire processes run independently on different CPU cores. Each type builds on the idea of executing more work at the same time to speed up the performance. This is the instruction level parallelism, which focuses on overlapping the execution of multiple instructions. The diagram shows a pipeline where there are different stages, which is fetch, decode, execute, memory, and write back. These are all working simultaneously but on a different instructions. This means while one instruction is being decoded, another one is executing at the same time, and the third might be writing its result. This overlapping increases instruction throughput, even though only one instruction completes per cycle. Then we have data level parallelism. It occurs when the same series of instructions is applied to multiple independent data elements. For example, applying an operation to every element in array. Since each data item can be processed independently, this allows parallel execution either on a vector processor or using multiple threads. This improves data throughput, the amount of data processed per
Um,
unit time.
Martin, I don't think we see your slides.
Oh, can you see it now?
Yeah, we can see it now.
Oh, come on. Can you see it now?
No, I mean, it still says data level parallelism.
Okay, let me see now. Hmm. Can you see now?
Yeah, we can see it now.
Okay. Uh, I'll go again from the instruction level parallelism. It focuses on overlapping the execution, as I said. There are multiple instructions that are working at the same time. One might be decoding, the other might be executing, and the third, fourth, or fifth might be writing the result. But each instruction completes is completed per cycle. That's what instruction level parallelism is. Then we have data level parallelism. So, uh, I, for example, applying an operation to every element in an array is also considered as data level parallelism. Since each data item can be processed independently, this allows parallel execution at the same time. This improves the data throughput. The amount of data processed per unit time is also improved at the same time. Then we have thread level parallelism. Uh, it divides the program into multiple threads, as you can see from the diagram. Even though a single CPU core executes one thread at a time, it switches between threads rapidly. This switching hides stalls like waiting for memory by running another thread during the delay. If there is a delay in this thread, then it will start running this thread. And once this is completed, then it will start working on it. So it switches continuously, due to which the CPU utilization stays high, making the processor more efficient at the same time. Then we have process level parallelism. It is the highest level of execution. Here, entire process run on separate CPU cores with its own address space and resources. Within each core, processes may also contain multiple threads. This level of parallelism drastically reduces execution time for heavy workloads because different tasks are handled independently across the cores. This also makes the processing time very uh, less and can give you the execution within seconds. Then we have process versus thread. So, a process is a fully independent program with its own memory, register, file storage, and network connections. Processes do not share memory by default, which is the main important concept of process. Then we have threads. Threads are subset of process, meaning that they share memory registers and resources, which makes them efficient for communication, but it also introduces synchronization challenges. Processes are great for compute intensive tasks. Threads are great for splitting small tasks inside one program. Then we have Amdahl's law. So it explains that the maximum speed up a program can achieve through parallelism. It states that the improvement is limited by the portion of program that must run serially. Even with the infinite processors, the serial part creates a performance ceiling. So at some time it gets stopped and it has reached its maximum output. The formula on the on over here shows that speed up depends on the fraction of serial executions and the number of parallel resources used. Then we have scaling. There are two different types of scaling. One is strong and one is weak. So strong scaling measures how much faster a program runs, keeping the program size the same. Weak scaling measures the performance when we increase the workload size proportionally to the number of processors, aiming to keep execution time stable. Both will help us to evaluate how well a parallel system handles increasing resource availability. Then we have context switch. It is important when switching between threads. So, what it happens is it saves the current state of thread after being stopped. Then it moves on to the next thread. But if it needs data from the previous thread, then it resumes the service at the thread ID, for example, and then get the data from it and then start a new thread. That's what context switch is. We have example threads. So The diagram over here shows four threads represented as a block of instructions. The gaps represent stalls, times when a thread is unable to execute due to waiting for resources like memory. So this is the gap between these two threads. By analyzing these threads, we understand that wherever the multi-threading comes, it helps fill in these gaps by running another thread during these stalls, and it ultimately improves throughput. Then we have fine-grained multi-threading. In this, the processor switches threads after every instruction. This means short or long stalls can be hidden because another thread always runs immediately. This the advantage of this is that we have a high throughput and we have very less idle time. The disadvantage is the slower execution for any single thread. There is a slower execution for any single thread because it gets interrupted constantly because multiple threads are running at the same time. Then we have coarse grained multi-threading. So the processor switches threads only when a major event occurs, such as a cache miss. This reduces the overhead of frequent switching. The drawback is that the shorter stalls cannot be hidden because thread switching only happens after big delays and not the small ones. Then we have simultaneous multi-threading. It allows multiple threads to execute in the same cycle on a single core by utilizing idle parts of the CPU. For example, modern processors like Intel's hyper-threading uses SMT. Its advantage is maximizing resource usage with minimal thread switching. The disadvantage of it is that it requires additional hardware and resource sharing management. We have what is multiprocessing and what is multi-threading. So multiprocessing uses multiple processors or cores, each executing separate processes or threads. We have multi-thread threading, which says that it uses a single processor to execute multiple threads concurrently by switching between them. Multiprocessing is ideal for heavy operations, whereas multi-threading is better for IO bound tasks when threads spend time waiting. We have computer architecture. It can be categorized based on how they handle instructions of data. First is SISD, which is one instruction, one data stream, typical for simple CPUs. Then we have SIMD, which is one instruction applied to multiple data items. It is commonly found in GPUs and vector processors. Then we have MIMD, which is multiple instructions operating on multiple data streams. It is used in modern multi-core systems. Then we have SPMD, which is a special case of MIMD, where each processor runs the same program but on different data. So, in SISD, only one instruction stream and one data stream exist. Performance improvements come from techniques like pipelining and multi-threading. But overall scalability of this is very limited. It uses less power but isn't suitable for large applications which requires parallel execution. Then we have SIMD. So all the processing units execute the same instruction but on different pieces of data. This is ideal for workloads like graphics rendering, matrix operations, and vector arithmetic. SIMD is much faster than SISD when operating on large data sets because it handles many data items simultaneously. Then we have MIMD. It consists of multiple process, each executing its own instruction stream on its own data. This gives maximum flexibility and is the architecture used in modern desktops, laptops, and mobile processor. It supports instruction level, thread level, and process level parallelism, but it requires more hardware complexity and communication management. Then we have SPMD. It stands for Single Program Multiple Data. In this architecture, the same program is executed on multiple processors, but each processor handles different data segments. SPMD is widely used in parallel programming frameworks like MPI and OpenMP, enabling scalable solutions for large data workloads. Then we have buses, protocols, and types of I/O. So these define how data moves inside a system and how components like processor, memories, and I/O devices communicate efficiently. They are essential for understanding overall system performance. So first we have communication. This slide shows communication within a computer system based on a Harvard architecture. The processor interacts with program memory and data memory separately, receiving instructions from one and data from the other. It also communicates with I/O device for input and output. Understanding these pathways will help us understand how efficiently data flows throughout the system. It also explains uh, the component communication, how each component communicates with each other. It emphasized that every major hardware unit, processors, memory, and I/O must coordinate effectively to avoid bottlenecks. Efficient communication is critical to achieve high performance in parallel systems. Set of rules to send and receive data. So it tells us how data moves between CPU and its memory subsystems. As parallelism increases, communication becomes even more important because multiple threads or processes may be requesting data at the same time, leading to potential congestions and delay. These are two different types of communications. Then we have types of I/O. Uh, how these different types of I/O interacts between the processor and external device. Although uh, the description is very minimal because the topic is very broad, but the each IO is depending on how much CPU involvement they require. Efficient IO handling prevents the CPU from wasting cycles waiting for slow devices. We have three different topics of IO over here. You can go through it in the recording as well. In this, it tells us about exception, interrupt, and polling, uh, and how they are raised and how they are executed, along with their advantages and example. We move to some of the questions. I'll keep the slide for 2 seconds for you guys to answer it, and as well as to see it in the recording as well. So first question is, which of the following best defines instruction level parallelism? Then we have a second question. According to Amdahl's law, the maximum speed up of a program is limited by. You can answer these in the chat, and the other two tutors would tell you if you are correct or not. Then we have questions on multi-threading, and also have questions based on differences between a process and a thread. Mm. Yeah. We have also questions on SIMD and MIMD architectures as well. And these are the answers that you can find at the end of the slides. So, do you guys have any questions? Just mail mail one of the tutors or come to the tutoring center, and we will be happy to help you guys with the questions as well.
All right. Thank you so much for attending this session. You guys can ask if you have any questions right now. Me and the other tutors are going to try to answer them. If not, this recording will be sent to your instructors and will be posted on Canvas.